I'm going to try to share some of our enthusiasm for this entire category. I can't tell you how excited I was to see the lineup of speakers here. I don't know if I've ever seen such a just inherently fascinating lineup. And then when I got here, the audience was, even more so. So it's a great honor to be here amongst you, and I look forward to many conversations afterward. What I want to share is a couple of caveats first are what I won't be able to talk about, which is how big companies get bigger. Don't know much about how that works, but I do work with people like this, the entrepreneurs that we invest in, that forge the future, really reinvent the world, and in some cases, like Elon Musk, try to reinvent other worlds as well. The ones on the left you may not know as well visually right now. Those are the founders of Nirvana, recently bought by Intel, one of our recent exits, and it was a deep learning chipset company that accelerates basically algorithms, hopefully that all of you can use, and if Intel doesn't mess it up, we'll continue to be able to offer that for you. And these are the people that we learn from. All the patterns and generalizations I'll share with you today should be credited in some way back to them, if they're good, and blame me if they're not. But really, they do the impossible. They take on large companies, they reinvent industries, and they, in a sense, are the vectors of progress in any meaningful sense. We try to focus on disruptive innovation in our business. Hence, I love the destruction in the lab name here, in the Clayton Christensen sense, in the Schumpeter sense. And in many ways, what they do is near impossible, and we should really celebrate them and just remind ourselves that's why we're here. Now, how many people know Ray Kurzweil's version of Moore's Law, the 100-year version of Moore's Law, it's sometimes called? I just want to see. Actually, keep your hand up for a sec, because everyone just does this. Okay, higher than usual, maybe 30% or less. The reason I'll show it briefly is I think it's a setup for everything that follows. It's what gives us hope in the future, and I think it's the most important thing ever graphed. What I'm showing on the axis here is something that you might actually purchase as a customer, like how much computational power does $1,000 buy. You could also plot how much storage can $1,000 buy. In either way, you get a pure exponential curve that transcends the integrated circuit. It has nothing to do with chips. There's nothing to do with Intel. In fact, Intel has lost the mantle for Moore's Law. NVIDIA has held it for the last 10 years in terms of where you can get the most price performance. Especially anyone in deep learning knows this, right? You've moved on long ago from CPUs. So you can plot, therefore, over long periods of time, and the gray bars vertically show you different technology epochs, from mechanical devices to census in 1890, the relay-based machine that cracked the Nazi Enigma code, if you saw the movie Imitation Game, and transistor-based computer that predicted Eisenhower's win. Now, if you plot the best price performance computer of the day on this, you see this incredible thing, right? Because this is a log scale. Every tick mark up the side is a 100,000-fold improvement. And you have this incredible curve. Excuse me, 100-fold, not 100,000. 100-fold improvement, 100x, another 100x, another 100x. None of these people knew they were on a curve. It's exogenous to the economy. Great Depression, World War I, World War II, recessions had no impact on humanity's capacity to compute. It just keeps compounding. It's kind of freaky, almost philosophical or cosmological. What is this about the vector of learning, the vector of progress? Everything you've heard about Moore's Law is a refraction of a longer-term trend that I won't get into today's talk because it's limited opening time, but I just want to keep in your mind, it's been going for 110 years. It might just happen to go for another 30. If it does, that's where you can get to some pretty wild predictions on the hardware substrate upon which AIs in the future would be built. It would be hard not to reach that. It then becomes a software problem. Just to let you know what these dots are, a variety of different companies that have come and gone. I don't even have the NVIDIA data, which, again, for the last 10 years would take the curve higher. And realize every one of these companies may have gone through their own S-curve. Every one of these companies had their own S-curve effects. But the technology vector, the baton keeps passing on. So yes, every given phenomenon has an S-curve, but technology and progress does not. It is compounding as an exponential, transcending and hopping across each of those S-curves. Now, what happens is that a variety of industries that were sheltered from competition become information businesses. They move from the crappy, low gross margin, work the sales channel to try to eke out an advantage kinds of businesses to something that's totally different. Think the automotive sector in transition now, or the aerospace sector in transition with SpaceX, for a current example of how the competitive response is to just fold, as opposed to literally reinvent themselves around software. These are the sectors we're currently investing in. Actually, for the last 5 to 10 years, we've been investing in these. And a lot of the perspective we gain comes from companies like Nirvana and others like that, D-Wave and others, who are selling tools to everyone else who's trying to do something meaningful in machine intelligence. We get a perspective into where the booms are happening because they're buying a lot of compute infrastructure. It'd be kind of like imagine you could sit at Amazon Web Services all day as an investor. It'd be pretty interesting if you invested in enterprise software. Let me go back to the result. A few years ago, based on what we were seeing in our portfolio companies, I came to the conclusion, at least personally, that machine intelligence, machine learning, deep learning, roll it all up. I like the word, by the way, I like Siobhan's use of machine intelligence because it's not yet overloaded with meaning, so we just say all that stuff that we're talking about today, not any one particular one. or subset or flavor, is the most important thing happening in technology as a trend. We were in this debate of venture capitalists, 5 of us, trying to eke out what are the 10 most important tech trends for the following 5 years, and this was back in 2013. And I posited that machine learning writ large is far and away, I thought, the most important thing for the future 5 years coming up. The VCs disagreed with me, but the audience, I got actually all their data, and 75% of the people in the audience, a cross-section of Silicon Valley at the time, thought that it's got a funny title, but basically machine learning is the future technology trend they agreed with. And I think that's been just crashing in a huge way all around us. As increasingly apparent that every industry will be touched by this phenomenon. And that's why it's important, I think, to understand it, especially for maybe some of the people in the audience who are just coming at this for the first time. So what is it? Just briefly, I won't go through this because I'm assuming most people know this, but the parts I want to emphasize that I think are interesting is the original analogy to the brain, I think, is telling. I'll come back to that later. Maybe even in the next panel we'll get into that a bit more. Because a lot of its derivative power, people keep relying on the existence proofs. Well, look what happens in the sensory cortex. Or if you want to ask the question, could a camera mounted on a car as the only sensor be a fully autonomous vehicle one day? And you just say, well, there's the existence proof. We do it all the time. So if one camera or 2 eyes can drive a car as the only sensor input, so should a robot of the future, but for the software, of course. So I think it's inspirational in many different ways. It's a learning machine. I think this is very important in that a lot of what I'm focusing on is learning. How do we, in a sense, parent or train complex systems of the future as opposed to engineer them? And I'll come back at the conclusion to that point again. It's a layered, iterative process, and I think when I say process, most of the learning is process learning. So if you're a practitioner of deep learning in a company or a manager of people who build this stuff, the things you learn are not the artifacts of creation, but the process of creation. Again, it's like parenting. If you raise a kid well, you don't understand the kid or tweak its neurons, right? The best you can do is offer advice to the next generation of parents on a very slow and glacial basis, of course. In the computer domain, think about that occurring much more rapidly. Often scrap the product of creation, start over with a better model, with some exceptions, of course, when you can layer these things. So I think there's important points. Process learning over product learning. Iterative algorithm. By the way, iterative algorithms are inherently computationally irreducible, I believe. Relying on some of Wolfram's work and some others. I believe that there's nor will there ever be a mathematical shortcut to the conclusion. And so that means there's a certain amount of embedded complexity, computational complexity in all these artifacts, and I don't think we'll ever find a quick shortcut around it. And lastly, maybe very important for human labor markets, is that the skills one acquires in these fields are very domain independent. This relates back to the process point. Imagine you could just build a better brain as an engineer, right? If you're just a really good brain builder, well, you could apply your trade wherever you most feel you have the most impact. We've recruited people out of Google on document translation to go work on cancer oncology and genomics, absolutely different fields. And the people that practice these fields take pride in the fact that they have no domain knowledge whatsoever. That actually helps keep them from being blinded by the specifics of what they're trying to build a brain around. But it also means the competition for labor markets is insane, right? You saw Auto getting acquired for a large sum of money, very painful to me as we were trying to negotiate the first round of financing for the company. Instead, right, they get acquired for a ridiculous amount of money per person. And the M&A and the acquisitions that large companies are making are averaging $6 and $10 million per head, right? Imagine $10 million a head, including the receptionist. I mean, everyone in the company. But that domain independence is both powerful in terms of people who can build better brains like Google will apply it all over the place and just run circles around companies who don't. I started this field, or started studying it and being fascinated by it in the 80s. I started a PhD. And back in 1989, took a class on this and was focusing on how to parallelize and trying to understand how to parallelize these neural network algorithms. I won't go into any of that other than it's the only textbook I saved from my undergraduate days. And it's still relevant in a lot of ways, but the terminology has changed and a few things have changed, and we now call it deep learning. Maybe, for some good reasons, because we've added many more layers. But in general, what has changed today is you have a lot of data, thanks to the internet. You have a lot of labeled data, thanks to the internet, so meta tags and such for training sets. And you have a mechanical Turk and other methods to add labels. So you just get a ton of data. And by the way, the word big data wouldn't be interesting if it weren't for machine learning, right? Big data would be big headache, right? Big data is beyond human understanding. It requires analytical techniques like what we're talking about today to make anything useful out of it. I think that's the future of engineering as well. Algorithmic advances, we'll be talking with Hinton at the next panel. There's been some major breakthroughs around 2012 and around the work of the people who really stuck with us when most people were naysayers in the 90s and early 2000s and made some important algorithmic advances, although opinions differ on how essential that was for the progress we've made. It's certainly important and one of the big three, I would say. And the last, of course, is just Moore's Law continuing, right? That that kerchunk, kerchunk, kerchunk of that earlier slide, it starts to add up. And if you look at the neural networks of the 80s to today, and by the way, the 80s led to kind of a dead end in the 90s where other than speech recognition, there wasn't much that neural networks were being used for. It's come quite a ways from there. Let's see if I can do a build. Yeah, so the neural nets of the 80s, 1 to 10 synapses, meaning the connections between nodes, kind of like analogous to the brain. Google Brain Project that found cats on the internet, just looking at YouTube videos, has about 1 billion. Interesting, orders of magnitude scale. But still a few steps away from a human. An adult is in the order of 60 to 100 trillion synapses in your brain, which, by the way, is 1/10 of what you had when you were born. So having too many, overwiring is just part of how we develop. The neurons that wire together, fire together, or actually vice versa. And that's how you prune into the brain that you have today. So, orders of scale. We'll just get there. That's hence the Moore's Law thing. It's not like we couldn't get there. That's the beauty of some of these systems. Now, the architectures are important. So let me go to that. Now, actually, before I do that, let me just mention, this is a little digression for just 1 sec. These are just examples of some of the companies that we saw. Oh my God, they're all using deep learning to drive core product development. So everything from the microbial design folks, the designers just raised a huge pile of money, re-engineering algae and other single-cell organisms to make chemicals and materials. People in the satellite imagery field who are interesting. It's missing a logo, but that's all right. Who already, because they're imaging the entire planet, every meter of the planet every day, they know human analysts can't look at the data like they used to before. So now they write algorithms to find roads, find new building construction, count every car in every parking lot of every retail outlet every day. Things like that. You wouldn't have humans doing it. Of course, you have to run smart algorithms on top of it. Risk assessment in financial services, cybersecurity, robots, of course, visual stuff, and I realize this is an older version of the slides, but that's fine. I was working on it during today. I'm kind of a procrastinator, so most of the work I did on my slides was today. There's a bunch of other ones in genomics that we're just investing in, but I don't have them listed here. Last one, drug discovery, is interesting. This little company, Atomwise, basically trained on ligand small molecule bindings. Basically, you want to, and this was work they did in Ebola. They found a drug that's now in animal testing. And what they found that was most interesting is that when they probed the nodes that they trained, again, with just a huge data set of known small molecule interactions, the deep learning network itself, when you probe various parts, learned the basics of chemistry, even though none of it was taught to it. The idea of a single carbon bond, the idea of atomicity in a molecule, and all kinds of other moderate to advanced chemistry concepts were embedded within the structure, which is kind of interesting that a body of knowledge just was created from a pairing of what works and what binds with what. Now, the thing I want to focus on that was after that digression was, how do we do what we do? And there's been an interesting migration in the computational substrate for deep learning, right? Almost everyone starts, as in many things, with a custom CPU. Computers are easy, they're fungible, you can set them up. The big breakthroughs, and many of the big breakthroughs occurred when people realized these things run really well on GPUs. Not because GPUs originally were designed for this. The vector math that it's included to do polygons and that matrix multiply that's embedded within there, actually it works pretty well for this kind of massively parallel computing. A little closer to the brain and how it's organized as opposed to a single processor, the way Intel's organized. FPGA work with Microsoft and a bunch of others have done some research to show you can do better than GPUs with an FPGA, which is a much more fine-grained architecture. Think of how do you split up transistors in memory, and if you just have like a fabric of them across a chip, it's a little closer to the way the brain maps still. And lastly, custom ASICs, right? Build a custom chip like Nirvana did and some other companies that we've seen 5 or 6 others that are in formation or building their first products. This is sort of an ultimate trajectory. If you want to do a really ridiculous amount of computational math, building a custom chip might be the most efficient way. In many ways, this is what the Bitcoin miners did, right? It's really peculiar today, by the way. I just got an update from my son who's really into this kind of stuff. Right now, the ASICs, the custom chips, are using the state-of-the-art Intel 12-nanometer fab process, and they today do more computation than all CPUs on Earth combined could do, just for Bitcoin mining. So the dedicated Bitcoin mining ASICs do more computation than all CPUs on Earth. And they consume as much power as Ireland every day. $2 million of energy a day. Now, if you look at this progression, one of the questions is, well, what kind of ASIC? And so there's an interesting split we're seeing. We've invested in Nirvana, digital, custom ASICs. We're about to invest, it hasn't closed yet, but in a few days here in an analog approach, which I'll show you just one slide on what that's all about. And then there's D-Wave, which we've heard about, in quantum computing. And oh, by the way, Google's been buying one of every D-Wave quantum computer since its formation and has signed a foreign contract to buy all of their next machines for the next 5 years. And they use it for quantum machine learning. And even in as early as 2009, they said outperformed their data center. And in recent results said that they can, in some specific test cases, achieve 100 million-fold speed up over traditional computers. So interesting to keep an eye on it. Now, What are some of these aspects? So let's look at analog for a moment. Analog is really interesting. Again, a little closer to the brain. The brain is not a digital computer. In fact, I love this quote from Jeff Hawkins on intelligence. I remember Barney and I went to a book club when that first came out. The brain, his big realization is the brain is not like a computer. It's the wrong metaphor. It's not like a homunculus in your head. It's not like the Industrial Revolution in your head. It's not like a digital computer in your head. It's a memory bank. The cortex, everything in it is a memory structure with a thin veneer of computation strapping it together. In fact, I would argue that the entire history of the semiconductor industry is recapitulating evolutionary biology, moving from a reptilian, limbic, logical brain to a just saturating with memory. The advance humans made over the primates was just more memory. It wasn't a new neuron. It wasn't a fundamentally different architecture, arguably other than the mirror neuron, but I don't think that really is the answer. I think just more memory and distributed memory. Now, how might you do something more similar to that in a chip? These guys, Isocline, have done something really fascinating. They realized you could take an off-the-shelf flash memory chip and make it into a matrix multiply and accumulate. It's the same math you would do digitally over and over again. And just to give you a simple example of how this can save you a ton of steps to do it in one, imagine you wanted to add up 100 numbers. Digitally, you'd have to have a register for each number, go through an iterative series of instructions to do add, accumulate, and you spit out an answer of many, many transistors, many, many steps. The way it works here is you literally run the analog signal of one number you want to multiply. The other one is already stored in the memory. You get a multiply for free, and the way you do addition of all those multiplies is all the wires just go to the same wire, so the currents just add up. It's like a physical addition of current gets you add for free without any clock cycle whatsoever. And so it's a frame-breaking kind of way to do this, and it gets about 100x performance advantage over digital approaches. Okay. Now, even more unusual, as I mentioned, was the possibility of quantum computers taking this on. And here's just a very rough generalization of what some of the digital or classical approaches, if you will, of computation are good at. Things like supervised learning, discriminative applications in a deterministic way, and are generally very parallelizable for GPUs, and that's one of the reasons it's running away so well. Though they can do things on the right side, but they're very hard, like a General Boltzmann machine, or some of the things in probabilistic programming where you want to sample from a distribution curve. Doing that digitally and actually creating a bunch of digital samples from a curve is difficult. What if you could actually look at the entire curve at once? What if you could look at an entire Ising model or graph, a probabilistic graph in one fell swoop and just have the answer pop out, kind of like all the currents adding up on a wire? What if you could look over a landscape to find the global minimum instantaneously by tunneling across states instead of testing valleys and doing gradient descent? That's part of the early work that's going on in quantum computing that shows, in fact, some of those things I just mentioned look like they're doable. This company out of Canada, Google just keeps saying breathless things about them. I don't know why Google's competitors don't wake up and say, God, what if Google's right? Like, what if actually this is like going to knock the socks off everything else? Like, maybe we'd want to buy one. Strangely enough, only Google has conviction and keeps buying, at least to date, in this category. So, neither Apple nor Microsoft has bought one. But we'll see. And I love their little cheeky, the known laws of physics, as if there might be unknown laws of physics that we should, try to tap into. I think I'll skip this one. This is just like, let's put it on a chip. We understand that. By the way, they're already manufacturing the 500. That's the best that actually, that's not true. Google has a 1K as well, but the 2K one is soon to come out. And this is the older version of the chart. I only wanted to show like any one of these four. These are just four different times they tested. Red was the quantum computer. Blue, classical algorithm, the PCD algorithm for finding again this minimum state in a probabilistic graph. And in a sense, the quantum computer does it naturally. It's like you want to see, is this collectively the best answer I can get? And what's fascinating is not only the red curves get to the best answers quicker, they also get the answers that blue classical algorithms may never get to, or in some cases they just go wandering off, hopping out of local minima and just getting completely lost in their search for the best answer. So let me just end with one last point, and then I think we'll try to leave some time for Q&A, so I won't use up all the time. This, I think, is kind of profound. It's something I wrote about in MIT Tech Review, I don't know, maybe 8-9 years ago, where everything I'd seen in what were then called neural networks and in all these other fields, like Steve Wolfram's analysis of cellular automata, or just biological evolution itself, or even directed evolution, as some of our microbial companies were using, genetic programming, which is a little branch of ways of sort of mating either code or algorithms to see if you can get a better match to a fitness function, kind of like evolution. And that little antenna that's being held in the fingertip is an example of one that NASA flew on a satellite where they have no idea why that antenna is the best for its analog function, but by, again, doing, in a sense, a series of permutations that I think Autodesk today would call generative design. That, by the way, that little thing in the bottom right corner that's going through is examples of what generative design often looks like. Very organic, very hard to do an obvious post hoc analysis like, well, that's why it's the best. You might be able to deduce in some of the simpler things they build. But once you scale up to very large trusses and harnesses, it's kind of peculiar. Why did in this physical space, this design do the best for the given challenge that they're putting to it? And of course, neural networks and deep learning. What they all have in common is that there's a set of iterations, right? And complexity accumulates, much like evolution itself, over this iterative algorithm. I don't believe there's any computational shortcut to the end. There's no way to run reverse evolution as information is lost at each step. And I think in all these cases, what's fascinating to me is that the artifact, the output, is therefore not predictable at the onset. There's no way, for example, in a cellular automata to say, given Rule 31, what will row 1000 converge to look like? Will it be chaotic? Will it be deterministic? You actually have to run the cellular automata all the way through, that's that sort of pyramid-looking structure you see up there, to know what the next row might look like. There's no way to hop to it. And to me, there's something almost poetic and beautiful about that, in that if much of the arc of evolution and learning, collectively as a group over eons embodied in culture, and now within learning machines, it's all about an iterative process of improvement. And now our machines, I think, are the main vectors of learning. They're training the other machines, whether it's our autonomous car companies training themselves in gaming harnesses, much like Grand Theft Auto, where they can drive billions of miles before they're actually on a real road. Now, I hope they don't pick up habits like in Grand Theft Auto, but they certainly can test some of the borderline cases, like staying on the road and off the sidewalks. Or if it's examples like AlphaGo playing other versions of the software, you can do better than the human in training the software. And I think this, again, focus on a process of learning. How do we build better brains? I think is one of the most important things going on in all of engineering and science right now. Well, I don't know about science and engineering. And in fact, there's a paper by Max Tegmark out of MIT recently that I think philosophically, I don't know if it's real science, but it's a wonderful philosophy. He claims it's real science, and I don't want to denigrate it in any way. I just don't know because it's so incredibly provocative as a paper that basically makes the argument that the reason that machine learning, deep learning, and neural networks are so powerful is that the physics of our world, the peculiar formula that are low polynomial order for almost any phenomenon, think about E equals mc squared, or any physics formula you've ever heard of, it tends to have low polynomials as opposed to any possible formula that would exist in the real world. And he makes the argument that everything that's a product of iterative algorithms shares some common computational similarities. And not surprisingly, our brain evolved to make sense of a very complex world. It was required by evolution to do a good job at making sense of vision and speech and complex pattern recognition in the presence of noise. All these things are inherently related to iterative algorithms, and so perhaps it's not surprising that if we model our computational structures on the brain, we might as well do well in those contexts. And I'm still looking and waiting for someone that can resolve what I thought might have been an ever-splitting dichotomy of design and evolutionary search or iterative algorithms, is that we're used to a Germanic sense of engineering. We build something, it does what we want. If it fails, it's a bug. Kind of like the Microsoft approach to programming. And then they just get a lot of bugs. I mean, Microsoft Office is larger than the human genome in just simple representation form digitally. It's full of bugs, right? It's just a mess. And now we want to build complex systems that transcend human understanding, that exceed the ability of any human to understand how they were designed or what they do. And yet we build those things today, and we increasingly will in the future. It's, I think, the future of engineering. I like a little summary quote Danny Hellis wrote in this computer science book called The Pattern on the Stone, his last chapter, where he thinks the greatest achievement, this was long ago he wrote this, because he didn't have the word deep learning. He didn't really know quite how we'd get there, but he just in his gut knew that we would find a way to transcend engineering in the traditional sense. And I would argue, and maybe I'll end with this provocative statement, that I believe machine intelligence, writ large, is the biggest advance in engineering since the scientific method. Right? It's a process advantage. Scientific method was a process advantage. I mean, God, Kevin Kelly, who's here, can remember how, in his books, how bad it was before when it was just like random seasonal variations in the weather gods, and you didn't know what you were doing when you're accumulating knowledge from intergenerationally, right? And then the scientific method allowed us, it was one of the best tools ever for society to learn how to learn better. I think it's almost a paraphrase of Kevin Kelly as well, I realize. And I do believe in the inevitability of certain technologies. In fact, everything I should just give a shout out. Everything Kevin Kelly's written, I think is fantastic, and Out of Control has been the most influential book on me of any that I've ever read. Yeah, there he is, yeah. Yeah. When I find myself just randomly spouting quotes of his, slightly incorrectly in the shower, then I know that it's had an influence. So he's here as well. We'll be wrapping up the day. So I just want to end with that. I think these are incredibly powerful technologies. I don't think most large companies realize how important this will be to their future and the future of engineering, and so they're scrambling and killing for talent. And I think that leads to a very exciting future. So let me leave it at that and say thank you. Yeah.